Hello and welcome to our discussion of circular and rotational motion, uniform circular motion, which is an extension of Isaac Newton's three laws and an extension of the concept of force. So, circular and rotational motion is very important because it shows and describes to us that we must understand the velocity at which an object that is moving in a circular motion must have different dimensions when compared to a body that is moving linearly, like you pushing a cart or a rocket that is flying out into space. Here you are rotating about an axis. And we must also understand the difference between rotation and spinning. Rotation and spinning. So many students have difficult time understanding the difference between rotation and spinning. Rotation is when you are moving around a fixed external axis. So you see, you have this CD, for example, that's the axis in the middle. All the points are rotating around this axis. So that's rotation. If you are going around a circular path, that shows you if you are maybe on a circular track and you are jogging around in a circle. That's an example of rotation. But spinning is when you have an internal axis. So you are spinning around yourself. So for example, if you look at the planets, the Earth revolves around the sun. That's an example of rotation because the sun is an external axis outside of Earth. So the Earth is rotating around the sun. But at the same time, to rotate from day to night, the Earth rotates around itself. So that's spinning. Spinning is when you are rotating around your internal axis, while in the external axis, you are rotating around an external axis, that's rotation, and rotating around an internal axis, that's an example of spinning. So all points on a CD travel in a circular path. They all move around a path. So these dots, these pits, along a line from the center to the edge, from the center to the edge, all move through the same angle. So now this angle here, that's the distance. Where we start, where we end, we have two distances. We have this angle here, and we have this arc length. So we covered this distance here. We have covered this. If we move from this position and the disc starts rotating, then stops here. This arc length would represent how far did this point get in a particular amount of time. Let's say in 5 seconds, the disk starts spinning from here, then stops. So in the time, the delta t would be 5 seconds, and my arc length would be known as delta s. So delta s would be how far did this point get from its initial position to its final position in about 5 seconds. The angle between the initial position and the final position is known as delta theta. So this delta theta is represented by dividing this delta S, the arc length, by the radius from the center of the circle to the outer edge on which we are rotating. That's r, that's radius. So if you divide the arc length, delta S, known as delta S, the arc length, if you divide that by the radius, that will give you delta theta. That will give you this angle here. What is the unit for that? Well, this is a very interesting problem because here you have the arc length. Is that time? That is not time. Arc length is not a time. Is length speed or velocity? Is not. Length is a distance. What about the radius? Is the radius time? No. Is the radius speed? No. The radius is distance also. So you have arc length delta S divided by the radius r. That's distance over distance. And that is going to be known as radian. So the unit for this angle representing this, the angle that is made by my initial and final position, this angle theta here is going to be delta S divided by R, which is known as unit radian. There we go. So the radius R is the axis, the beginning is the center of my circle. And the radius r of a circle is rotated through an angle theta. The arc length is delta S, and that is the distance covered along the circumference from my initial point to my final point. And the law says if I want to figure out numerically what is the value of this angle that we rotated to, we have to divide the arc length, known as delta S, by the radius r. What unit is that? That is radian. So point 1 here and point 2 rotate the same angle, but point 2 moves through a greater arc length because it is farther from the center of rotation. Let's say this is my CD. I have a point here, and I have a point on the outside too. Well, that's very interesting. If we start spinning our CD, then stop here, our second point will be right at this point, and our first point will be here. The angle is the same. The angle is the same. The time it took to cover this distance is obviously the same. But what is different? What's different is the length, the arc length. Obviously, the point that was closer to my center had a shorter, smaller radius. Therefore, we're not moving in the circumference, we're moving inside. So that will show a smaller arc length, and that on the outside, we will have a longer arc length. So we should know that the farther we go away from the center, the more arc length we will cover at any moment in time. So if I need to figure out this angle, theta, I have to divide my arc length by my radius. That is no problem because the bigger the arc length, the bigger the radius. So the ratio will be conserved. So a car moving at a velocity v. So the car is moving. Here, the car is moving. We're not talking about the movement of the wheel. We're talking about the car moving from west to east, moving in the eastern positive direction. Has a tire rotating with angular velocity omega. There we go. Now the speed of the circular tire is different than from the speed by which your car is moving, and that is known as omega. So the speed of the tread of the tire here at the circumference relative to the axle, that is the axle, the center, known as so the axle is moving with speed v because the axle is part of my car. So my car is moving with velocity v, and so is my axle. My bumper, me, the wheel, the engine, we're all moving at the same velocity v. It is the tire who's spinning in circle. The tire is rotating around the axis. We're not rotating. So there's two different velocities here. There's the velocity of the car moving, and there's the velocity of the wheel spinning. So you have to differentiate them. The velocity of the car moving is known as V, and the velocity of the wheel spinning is known as omega, So the same as if the car were jacked up and the wheel spinning without touching the road. So the speed of the tread of the tire relative to the axle. So directly below the axle, where the tire touches the road here, the tire tread moves backward with respect to the axle with tangential velocity. So if I need to know the tangential velocity of my, if I need to know the tangential velocity of my wheel, I have to multiply the radius, which is the distance from the center of my circle to where the point ends. And I have to multiply the radius by omega. And then if I usually we ask for omega, which is the velocity of the tire spinning, and we divide that by the radius, that will give us omega, where r is the radius. And because the road is stationary with respect to the point of the tire, so the road here is not moving. The car must move forward at a linear velocity. That's a linear velocity v. So a larger angular velocity for the tire means a greater linear velocity for the car. So the more tangentially, so the tangential velocity, that is known as the linear velocity at any point. So the velocity here point in this direction because the wheel is spinning. Here pointing in this direction, here pointing in that direction, here pointing in this direction. So we are spinning in directions that are bringing us toward the center. So the faster this tangential velocity is, the faster our car is going to move in the forward linear direction. There we go. So here the velocity, we know velocity is a vector, is going to point in this direction. Here the velocity is pointing in this direction. Here the velocity is pointing in this direction. So if we had a fly here, it says as the fly on the edge of an old-fashioned vinyl record moves in a circle, its instantaneous velocity is always at a tangent to the circle. So the direction of the angular velocity is into the page, as in here. So the omega is the speed by which the circular motion is. And we said, how do we calculate omega? We calculate omega by dividing the velocity by which the wheel is spinning. We divide the velocity by the radius, and that will give us the actual angular velocity. So if we examine here, the direction of the velocity of an object at two different points are shown here. The direction of the velocity of an object at two different points are shown. And the change in velocity, known as delta V, is seen to point approximately toward the center of the curvature. So for an extremely small value, known as delta S, delta V points exactly toward the center of the circle. So the net velocity is always going to be the sum of the two velocities that are adding up. So I have at this point B, my velocity is pointing in this direction. At this point C, my velocity is going to point in that direction. If I add them together, the net velocity is always going to be pointing to the center, leading to a centripetal acceleration, accelerating towards the center. And we know that delta V, this net velocity, divided by the time it took us from our initial time to our final time that took us in this arc length, we're going to divide that centripetal velocity, we're going to divide that net velocity by that net time to give us the centripetal acceleration that is pointing towards the center. So if you look in this figure, the frictional force F here, this frictional force F, serves as the centripetal force. So this is the force that is pushing my object to remain in that uniform circular motion. And the centripetal force is always perpendicular to the tangential velocity. So this is my tangential velocity. The tangential velocity represents the instantaneous velocity at which this point is moving while we are in a uniform circular motion. So the larger the centripetal force, the smaller the radius of the curvature and the sharper the curve. So the lower the curve, so the lower curve has the same velocity, but a larger centripetal force, producing a smaller radius. So you see, the more the force pushing against the point towards the center, the smaller our radius. So that's a force that is pushing towards the center. If you are driving your car and you come closer to the curve, you feel that you are moving away from the center of your car. That is known as the centrifugal force. So here we see that the centripetal force here is equal to the centripetal acceleration, since we know that the centripetal force is equal to the mass of this object at this point that is going with this velocity and multiplied by the acceleration that enables this point to move in the circle. So here we see a car that is going around this circular path. We see that there is a centripetal acceleration that is pushing the car towards the center, and the distance from your system, the car, towards the center, that is the radius. And the velocity, the tangential velocity at this point represents the instantaneous velocity that this car is moving at in this location. So here you see this car is moving, for example, into the page. It's undergoing a weight force that is pushing it downward, and there is a normal force that is opposing this gravitational force represented by the mass of the person and the car multiplied by gravity minus 9.81. And opposing to that would be the normal force. And then there is friction on the tires. This friction on the tires is going to equal the centripetal force. Centripetal force here is going to be equal to the coefficient of friction, that is what is the material from which the tire is made, multiplied by the normal force, that is holding the car from plummeting into the weight force that is pushing the car downward. So that's an example of spinning. So here the skater spins in a counterclockwise. So her angular velocity is normally considered to be positive. If you move counterclockwise, that's a positive position. So that's a positive velocity if you move counterclockwise. If you move in a direction that is clockwise, that is known as the negative direction. So a question on the exam would be, if a skater spins in the counterclockwise, is that known as positive or negative? So people think that clockwise is the normal thing, so that should be positive. No, the clockwise direction is the negative direction, while the counterclockwise is the positive direction. So that's spinning. So we're not rotating around an external axis. Here we are spinning around. We are spinning around a internal axis. Tornadoes descend from the clouds in a funnel-like shape. That's spinning. So we are spinning here in this tornado inside an internal axis. So when you look at the merry-go-round, that helps us to understand the torque. So the torque will increase if you apply a perpendicular. If you apply the more perpendicular the force, the more perpendicular the force applied at an object at a 90-degree level, the more force that this object is going to withstand. If this person was not at a 90-degree angle and on the side, they're not getting the best worth, or they're not making the merry-go-round spin as much as it should. But if they align themselves in a perpendicular angle to the radius of the circle, then that will maximize the leverage. So here a man pushes a merry-go-round at its edge and in a perpendicular line to the lever arm that will help achieve the maximal that will help us achieve the maximal help us achieve the maximal torque. So torque is the force that is applied at a perpendicular line. So if you have ever spun a bike wheel or pushed a merry-go-round, you would notice that the force needed to change the angular velocity. So you can control the spinning of that object. So the farther the force is applied from the pivot point, known as the fulcrum, the greater the angular acceleration. So for example, a door opens slowly if you push too close to its hinge. But if you push the door all the way from the outside, so where the knob is, let's say you open the door and then you slam the door as hard as you can from the knob, the door is going to make a really loud sound. But if you push with the same force, but not at the knob, at the middle of the door, you see that the door would move more slowly. And if you push with the same torque, but not in the middle of the door, more closer to the hinge, you will see that even though the same force led the door to slam really hard, that now that you would have a difficulty even trying to shut the door. So the farther you move away from that hinge, from that pivot point, the farther you move away from the fulcrum, the farther so this is the fulcrum, that's the pivot point. The farther you move away from it, the more force, the more perpendicular you are, and the farther away you are from the center, the more maximal the torque will be. But if the person was maybe applying force to the middle point, the merry-go-round would spin, but not as much as it would in the farthest point. So the farther you are, the better. You know, a baseball bat, if you hit the baseball with the farthest tip of your baseball bat, you're more likely to have a home run than when you hit it with the middle of the baseball bat. And so here we need to appreciate that the more perpendicular the hit is, the farther the stronger the torque will be. So this here shows us a solenoid, and in the solenoid, we can see that there is this shows us actually a fishing reel. So if we want to stop the fishing reel, so the magnitude of the initial angular velocity, we have to recognize the magnitude of the initial angular velocity, and the final angular velocity has to be 0 because we want to stop spinning, because we caught the fish and we want to be able to stop rolling it backward. So the magnitude of the angular acceleration, in order to get that, we have to recognize that our angular velocity is going to equal to our initial velocity, is going to equal our initial angular velocity, our final angular velocity at which we are spinning this reel, this fishing reel. The final angular velocity is going to equal to the initial angular velocity we started with. So the final angular velocity has to be zero. We're going to have a zero equal the initial angular velocity, which is the one that's going really fast. Maybe it's going at minus 300 radians per second. And we're going to add to that the acceleration multiplied by the time of this entire, the time of the entire period that is going to allow us to coil back this reel here. So you know that acceleration equals velocity divided by time. If we multiply acceleration, the acceleration by the time, we're going to get our velocity, and we add that to our initial velocity, and that's going to give us the final omega. It's going to give us the final omega, the final angular velocity, which will be zero in this case because we're going to stop rotating the wheel.